Okay, so today I would like to discuss about the properties of optical fiber transmission. So signal loss and system bandwidth basically describes the amount of data that is transmitted over a specified length of fiber. Now, many optical fiber properties increase signal loss and also reduce the system bandwidth. Now, the most important properties that affect system performance are fiber attenuation and dispersion. Okay, so attenuation reduces the amount of optical power which is transmitted by the fiber, and it controls the distance an optical signal pulse can travel. Uh, so that is shown over here, and once the power of an optical pulse is reduced to a point where the receiver is unable to detect it, the actual pulse, and error occurs. So this attenuation is mainly a result of light absorption, light scattering, and also the bending losses. Now, in case of dispersion, it spares the optical pulse as it travels through this fiber. Now, this spreading of this signal pulse reduces the system bandwidth or the information carrying capacity of that fiber, and it limits how fast information is transferred. Okay, so an error occurs when the receiver is unable to distinguish between the input pulses, which is caused by the spreading of each pulse, and that time the error will be occurred. So the effects of attenuation as well as this dispersion increase as a pulse travels the length of the fiber. So instead of this attenuation and dispersion, other optical fiber properties also affect the system performance. Now, like for example, modal noise is there, pulse broadening and polarization. So this can reduce the system performance also. Okay. Now, attenuation, what is it? This attenuation is the loss of optical power as light travels along the fiber. So signal attenuation, that is defined as the ratio of optical input power to the optical output power. Optical input power, that is the power injected into the fiber from an optical source, and optical output power, that is the power received at the fiber in or optical detector. Now, this equation describes the definition of this attenuation, where L is the length which is expressed in kilometers, and therefore the unit of this attenuation is decibels per kilometer. Okay, so basically this is caused by the absorption, as I have told you, scattering and the bending losses. So each mechanism of loss is influenced by the fiber material properties and the fiber structure also. However, this loss is also present at fiber connections also. Now, move on to the next slide, which is absorption. Okay, so absorption is a major cause of signal loss in an optical fiber, and it is what is this? So it is basically the portion of attenuation resulting from the conversion of optical power into another energy form, such as heat. So absorption in optical fiber, that is explained by three factors. First one is the imperfections in the atomic structure of the fiber material. Second is the intrinsic or basic fiber material properties, and the last is the extrinsic fiber material properties. So extrinsic means the presence of impurities. Now, imperfections in the atomic structure which induce absorption by the presence of missing molecules or oxygen defects. So absorption is also influenced or induced by the diffusion of hydrogen molecules into the glass fiber. And these intrinsic and extrinsic material properties are the main cause of absorption. So what is intrinsic absorption? Intrinsic absorption basically that is caused by the basic fiber material properties, and if an optical fiber were absolutely pure with no imperfections or impurities in inside them, then all absorptions would be called as intrinsic. And also says the minimal level of absorption. So in fiber optics, silica or the pure glass fibers are used it as intrinsic material, and silica fibers are used because of their low intrinsic material absorption at the well-being of this population. The main cause of this intrinsic absorption in the infrared region, that is the characteristics vibration frequency of atomic bonds. Now in silica glass, what happened? The absorption is caused by the vibration of silicon oxygen bond is there, and the interaction between the vibrating bond and the electromagnetic field of the optical signal, it causes the absorption, intrinsic absorption. And in case of extrinsic absorption, that is caused by the impurities induced to the fiber material. Trace metal impurities such as iron, nickel, chromium, these are introduced into the fiber during fabrication. Okay, and this type of absorption is caused by the electronic transition of this metal from one energy level to another, and it occurs when the hydroxyl ion are introduced into the fiber. The amount of water impurities present in a fiber, that should be less than a few parts per billion, and this fiber attenuation caused by this intrinsic type absorption, that is affected by the level of impurities hydroxyl ion which is present inside fiber. Now if the amount of impurities in a fiber is reduced, the fiber attenuation is also reduced. Next is the scattering. So basically scattering losses are caused by the interaction of light with density fluctuations within a fiber. Density changes are produced when optical fibers are manufactured. Now, during manufacturing process, regions of higher and lower molecular density areas relative to the average density of the fiber are also created. Light traveling through the fiber interacts with the density. You can see here light is actually after it is given inside this fiber, it is actually scattered in all directions. Now in what happened in commercial fibers, the main source of loss basically is called the relic scattering. Relic scattering occurs when the size of the density fluctuations is less than 1/10 of the operating wavelength of the light. Now, this loss, which is caused by the Rayleigh scattering, is also proportional to the fourth power of wavelength. If the wavelength is lambda, then it will be given as 1 by lambda to the power 4. Now, as the wavelength is increased, loss caused by this scattering method also decreases. Decreased. Next is the bending loss. So bending the fiber. So bending actually it causes also attenuation, and it is classified according to the bend radius of the curvature, like micro bend loss is there, macro bend loss is there. So micro bends are small microscopic bends of the fiber axis that occur mainly when a fiber is cable. Now macro bends are bends having a large radius of curvature relative to the fiber diameter. Now, micro bend and macro bend, both losses are very important loss mechanism in fiber optics, and fiber loss that is caused by the micro bending that can still occur even if the fiber is cabled correctly. Now, during installation, what you need to do that if fibers are bent too sharply, micro bend losses will occur. Sorry, macro bend losses will be occur. Now, micro bend losses are that is caused by small discontinuities or the imperfections in the fiber. Now, uneven coating applications and improper cabling procedures is this micro bend loss. Another maybe like this external force. This is also a source of micro bends. External force deforms the cable jacket surrounding the fiber, but causes only a small bend in the fiber. Okay, and also it changes if it occurs, it changes the path that propagating moves. Micro bend loss actually it increases the attenuation because of low order modes become coupled with the higher order modes, and that are naturally losing. And in case of macro bend loss, what happened? These are observed when a fiber bend's radius of curvature is large enough compared to that fiber diameter. So these bends become a great source of loss when radius of curvature is less than several centimeters. Okay, so now what I need to do to maintain the phase of the light wave, mode phase velocity must be increased, and when the fiber bend is less than some critical radius, the mode phase velocity must increase to a speed that is greater than the speed of the light. However, it is impossible to exceed the speed of light. Now, this condition causes some of the light within the fiber to be covered to higher order modes. Now, these higher order modes are then lost or radiated out of the fiber. Now, this fiber sensitivity bending losses that can be reduced if the refractive index of the core is increased, then fiber sensitivity decreases. Okay, sensitivity also decreases as the diameter of the overall fiber that will be increased to a certain position. So increases in the fiber core diameter, that also increases the fiber sensitivity, and fibers with large core size that propagate more modes. Next, the dispersion. So there are two types of dispersion in optical fibers. One is called intramodal or chromatic dispersion. Another is called intermodal or modal dispersion. So each type of dispersion mechanism that leads to pulse spreading. Okay, so as a pulse spread, energy is overlapped, as you can see here in this picture. Now, this spreading of this optical pulse, as it travels along the fiber, it limits the information capacity of the fiber. Now, in case of intramodal or chromatic dispersion, it depends primarily on the fiber materials. There are two types of intramodal dispersion. The first type is the material dispersion, and second is the waveguide dispersion. Okay, so intramodal dispersion, it occurs when, because different colors of light travels through the different material and different waveguide structures at different speeds. So material dispersion basically occurs because the spreading of the light pulse is dependent on the wavelengths which interacts with the refractive index of the fiber core. Different wavelengths travel at different speeds in the fiber material. Different wavelengths of a light pulse that enter a fiber at one time exist. It exit the fiber at different times. So material dispersion is a function of the source spectral weight, and that source spectral weight specifies the range of wavelengths that can propagate in the fiber. And it will be less, this material dispersion will be less if in case of longer wavelengths. Now, other is the waveguide dispersion, which occurs because of the mode propagation constant, that is a function of the size of the fiber core relative to the wavelength of the operation. Now, waveguide dispersion that is occurs because of the light propagates differently in the core than in the cladding. Okay. So in multi-mode fiber, what happened? This waveguide dispersion and as well as this material dispersion, both are basically these are separate properties. So in multi-mode waveguide dispersion is generally small compared to material dispersion, and this waveguide dispersion usually neglected at that time. But in case of single mode fibers, material and waveguide dispersion are interrelated. The total dispersion present in single mode fibers may be minimized by trading material and waveguide properties depending on the wavelength of the operation. Okay. Second is the intermodal or modal dispersion. What is that? Why it is happened? Because of the input light pulse spread. Input light pulse is made of a group of modes. As the modes propagate along the fiber, light energy distributed among the modes, that is delayed by different amounts of time. Now the pulse spreads because each mode propagates along the fiber at different speeds. Since modes travels in different directions, some modes travel longer distances. Now modal dispersions occurs because each mode travels at different distance over the same time span, like this it is given here. So this condition causes the light pulse to spread. As the length of the fiber increases, so modal dispersion also increases, and it is the dominant source of dispersion in multi-mode fibers. It does not exist in single mode fibers. Single mode fibers propagate only the fundamental mode. Therefore, single mode fibers exhibit the lowest amount of total dispersion. Also, it exhibits the highest possible single mode. So optical fiber connectors. So connectors are mechanisms or techniques used to join an optical fiber to another fiber or to a fiber optic component. Now it terminates the end of an optical fiber and enables quicker connection as well as the disconnection. Now the connectors mechanically couple and align the codes of the fiber so light can pass. Better connectors are it loses very little light due to reflection or misalignment of the fibers. Okay, there are lots of connectors present in market. So these are the pictures of different connectors. So this is a flexible device that connects the fiber cables, repairing a quick connection and the disconnection. The optical fibers terminate fiber optic connections to fiber equipment or join two fiber connections without the splicing. Now, hundreds of optical fiber connector types are available, but the key differentiator is defined by the mechanical coupling technique and dimensions. The optical fiber connectors ensures stable connections as they ensure the fiber ends are optically smooth and the end-to-end positions are properly timed. Okay. Now the main components of this type of connectors are a ferrule, sub-assembly body cable, and stress release boot, and also the connector housing. Okay. So ferrule is mostly made of hardened material like stainless steel, or it can be tungsten carbide, and also it ensures the alignment during the connector mating. So the connector body that holds the ferrule and the coupling device serves the purpose of male-female configurations. Okay, the fiber types for fiber optic connectors are categorized into different connectors for simplex mode, for duplex mode. Okay, and for there are multiple fiber connectors are available. Now simplex connector has one fiber terminated in the connector, whereas duplex has two fibers terminated in the connector. Now multiple fiber connectors can have two or more fibers, as it names. Now optical fiber connectors are dissimilar to other electronic connectors in that they do not have a jack and plug design. Okay, instead they make use of the fiber mating sleeve for connection purposes. So there are certain principles for making a good connector, like low coupling loss, interchangeability, means no variation is loss whenever a connector is applied to a fiber, and ease of assembly, low environmental sensitivity, low cost. Connector should be in the inexpensive. Okay, reliable operation, ease of connection, and also the repeatability. So the connection and reconnection many times without an increase in loss. So it will be better in that case. So common optical fiber connectors include this type of connectors, like biconic connector is there, B4 connector is there, SCON, FC, FDDI, LC connector, SC connector, MTRG connector. So basically this biconic connector, these connectors use precision tapered ends to have low insertion loss. And D4 connectors have a keyed body that is very easy for intermediate. Okay, and ISCON. So this type of connectors are commonly used to connect from a wall outlet to a device. Okay, FC connectors are there, like these are actually fixed connector type device, which is used for single mode fibers and for very high speed communication. Okay. FDDI, this type of connector is a duplex connector which makes use of fixed type of device. Okay. LC connectors are these are called local connection connector. It has the benefit of small form factor optical transmitter or receiver assemblies, and is largely used in private and public networks. This LC type connector. Okay, SC type connector is connector actually called the subscriber connector. SC means subscriber connector, that is used in simplex and multiple applications, and is best suited for highly very high density applications where it is needed. Okay. Next is the fiber splices. So permanent or semi-permanent connection between two individual optical fibers is known as fiber splice, and the process of joining these two fibers are called as splicing. So typically a splice is used outside the buildings, and connectors are used to join the cables within the buildings. So splices offer lower attenuation and lower back reflection than connectors, and are very less expensive. So there are two types of splicing. One is called fusion splicing, another is the mechanical splicing or V group. So what is fusion splicing? It involves basically it butting two clean fiber end faces and hitting them until they melt together or fuse. So this is normally done with a fusion splicer that controls the alignment of the fibers to keep losses as low as much possible. So fiber ends are first pre-aligned and butted together under a microscope with micro manipulators. Then the butted joint is heated, and so it is heated with electric arc or laser pulse to melt the fiber ends, so they can be bonded together. Okay, so here is the diagram for fusion splicing. Then the mechanical splicing or V group. Here it join two fibers together by clamping them with a structure or by epoxying the fibers together. Now, the mechanical splices that may have a slightly higher loss and back reflection compared to this fusion splicing. This can be reduced by inserting index matching gel. So V groove mechanical splicing provides basically this temporary joint, that is fibers can be reassembled if required. The fiber ends are butted together in a V-shaped groove, as it shown over here. You can see it. Now the two types of fiber optic splices, these are used in different applications. The mechanical one that is used for applications where the splices need to be made very quickly and where the expensive equipment for fusion splices may not be available. Now, some of the slips for mechanical fiber optic splices are there for and the connection and disconnection purpose. So in this way, the mechanical splice may be used in applications where the splices may be of less permanent. Now, fusion splices over a lower level of loss and have very high degree of performance. Now, they require the use of the expensive fusion splicing equipment here. That is the disadvantage of having this type of splicing method. Now, so in view of this, they tend to be used more for the long high data rate lines that are installed, that are unlikely to be changed once installed. Okay, so these are the topics which I have covered today. So that's all for today. If you have any question, any doubt, you can ask me.